Welcome to today's deep dive. So usually when a sprawling flat city runs out of land to build on, the solution is pretty obvious, right? You stop building outward and you just start building upward.
Yeah, exactly. You just build skyscrapers.
Right. And that is exactly what Huawei is claiming to do with microchips. Today, we're looking at a breakdown from Anastasi in Tech to figure out if Huawei's new method for hitting 1.4 nanometer class performance.
Without using advanced EUV lithography machines, I should add.
Yes, exactly. Without those machines, we're trying to figure out if this is, a genuine computing revolution or just a really elaborate workaround.
Right, because to understand why Huawei is taking this vertical route, we kind of have to look at the wall that TSMC and everyone else is hitting with Moore's law.
The shrinking problem.
Exactly. Shrinking transistors it's failing. I mean, even an industry giant like TSMC is fighting tooth and nail right now for a mere 6% area gain in their upcoming generation.
Hey, only 6%.
Yeah, just 6%. And what's fascinating here is the bottleneck isn't even the computation itself anymore. According to Huawei's data, over 80% of a chip's energy is spent literally just moving data around.
Okay, let's unpack this. Are you saying a multi-billion-dollar data center is basically just a giant, exhausted courier service?
I mean, yeah, essentially. It all comes down to RC delay. Modern chips have these massive networks of metal wiring, and the physical resistance of those wires
slows the signals down.
Exactly. Slows it all down. Plus, you have capacitors acting like, parasitic batteries. So the longer the journey across that flat 2D chip, the worse the energy drain becomes.
So instead of trying to optimize that flat space, Huawei is trying to master time. By using this method called taco scaling, they're physically folding logic checks on top of each other.
Right, building those skyscrapers. So the data only has to travel a few microns vertically instead of millimeters horizontally.
Here's where it gets really interesting, though. Taking two logic chips and folding them isn't just like snapping Legos together, right?
Oh, not at all. You have to use hybrid bonding. This means you physically fuse the microscopic copper pads of two separate chips together to make one seamless connection.
And that is an absolute manufacturing nightmare. I mean, the current state of the art for companies like AMD and Intel is what, about a 9-micron pitch?
Roughly 9 microns.
But Huawei is targeting an incredibly aggressive 1.5 microns. How do you perfectly align millions of microscopic wires without massive defect rates?
Well, that is the multi-billion-dollar question. If you miss that alignment by even a fraction of a micron,
it just shorts out.
Yep. The connection shorts out and the entire chip is just garbage. So hitting a 1.5 micron pitch means they need near perfect control across the entire silicon wafer.
But wait, even if they nail the alignment, building a denser city means you run into a fundamental physics problem, right? Like the heat.
Oh yeah, thermal density. It's totally different from passive memory stacking.
Because passive memory runs pretty cool.
Yeah. Exactly. But active logic generates massive temperatures. If you stack those hotspots vertically on top of each other, the heat just gets trapped right in the middle layers.
With nowhere to go. So it would just instantly thermally throttle, ruining all those performance gains.
Pretty much, yeah. A data center can throw giant heat sinks and liquid cooling at the problem, but
Huawei wants to put this in a Kirin smartphone processor. If they do that, how does it not literally melt in your hand without a data center's liquid cooling?
That is their ultimate thermal trap. Without a massive breakthrough in heat dissipation materials, a mobile chip just can't sustain peak performance in that architecture.
So when we look at the realities of the engineering, it really clarifies their 1.4 nanometer claim. By stacking older, mature nodes, they estimate they can hit 238 million transistors per square millimeter.
Right. If we connect this to the bigger picture, it's an equivalent of a 1.4 nanometer chip in terms of density, not a true microscopic shrink of the transistor itself.
Which is like a 55% density boost over flat designs.
Exactly. They're basically trading much higher manufacturing and packaging costs to get leading-edge performance without needing those leading-edge EUV machines.
So what does this all mean for you listening? Well, it means the future devices in your pocket will likely rely on these crazy 3D architectural tricks rather than just, microscopic shrinking.
Definitely. The 2D era is kind of ending.
But it leaves us with this pretty wild thought to mull over. If these 3D skyscraper chips inevitably create unmanageable heat for handheld devices, are we heading toward a future where smartphones have to abandon onboard processing entirely? Where every demanding app we use is forced to run remotely from a liquid-cooled data center?